Today we have planned to discuss another single source shortest path algorithm. Now I am not disclosing the name of the algorithm. First of all, let us assume that we have a weighted directed graph G, which is represented as V, E. Suppose you have this graph. And if you analyze the graph, you will find here 1, 2, 3, 4 and 5 vertices and a number of edges associated with this graph. And what are the edges? S to T there is an edge, S to Y there is another edge, S to T, S to Y. Then there is no edge from S to other two vertices X and Z. Then T to X there is an edge, T to Y there is another edge, and T to Z there is another edge, T to X, T to Y, T to Z. There is no direct edge from T to S. Then X to T there is an edge, X to T. Similarly, Z to S there is an edge, Z to X there is another edge, and Y to X there is an edge, Y to Z there is an edge. If you compare the values of the edges, that means weight of the edges, 6 is an edge weight which is less than another edge weight 8, 7 is another edge weight which is greater than 6, 2 is another edge weight which is less than 7, etc, etc. But in this graph there are 3 edges, one from T to Z, second one from X to T, and third edge is from Y to X. If you analyze these 3 edge weights, these 3 edge weights are negative. So 3 edges, T to Z, X to T and Y to X, are holding negative edge weights. Assuming that in this graph you are asked to apply single source shortest path algorithm considering S as a source, then as in this graph some edge weights are negative, so you cannot apply Dijkstra, because you know that Dijkstra never allows unweighted directed graph having negative edge weight. So what is the alternative? Another algorithm is there which is called the alternative here. This is Bellman Ford algorithm, which allows negative edge weights, -2, -3, -4. So we can solve this graph using Bellman Ford algorithm, which is also a single source shortest path algorithm, which allows negative edge weights. Now suppose you have a very simple graph. Suppose 1 is the first vertex, 2 is the second vertex, and 3 is the third one. Okay, and assuming that it is also a directed graph. Suppose there is an edge from 1 to 2, and suppose there is an edge from 1 to 3. Similarly, suppose there is an edge from 2 to 1, and suppose there is an edge from 2 to 3. Suppose there is an edge from 3 to 1, and assume that there is an edge from 3 to 2. So this is an weighted directed graph, though I am till now not applying the edge weights. Suppose some edge weight is given, some edge weight is given, some edge weight is given, and so on. Assuming that it is a directed graph, and also assume that I have provided some edge weights, though I am not representing here the weight parameters values, but assume that the edge weights are also given. So in this graph there are 3 vertices. Suppose n is the number of vertices, n equals to 3. So what is n minus 1? N minus 1 means 2. 3 minus 1, 2. If you consider vertex number 1, so there is an edge from 1 to 2, and there is an edge from 1 to 3. Similarly, if you pick up vertex number 2, there is an edge from 2 to 1 and there is an edge from 2 to 3. So 2 to 1 there is an edge and 2 to 3 there is an edge. If you pick up vertex number 3, 3 to 1 there is an edge, 3 to 2 there is another edge, 3 to 1 and 3 to 2. I am talking about the direct edge, 3 to 1, 3 to 2. So with respect to vertex 1, it is covering total 2 edges. With respect to vertex 2, it is also covering total 2 edges. With respect to vertex 3, it is also covering total 2 edges. So it concludes, if a graph consists of n number of vertices and if all vertices are connected to each other, like this one, 1 to 2, 2 to 1, 1 to 3, 3 to 1, 2 to 3, 3 to 2. That means if all the vertices are connected to each other, then each vertex can cover n minus 1 edges, where n is the total number of vertices. In this graph, n means 3, n minus 1 is 2. So for vertex 1 can cover 2 edges, 1 to 2, 1 to 3. Vertex number 2 can cover 2 edges, 2 to 1, 2 to 3. Vertex number 3 can cover 3 to 1, 3 to 2. So in a graph, if it is a directed graph, suppose, if total number of vertices be n, then each vertex can cover at most n minus 1 edges. Similarly, if you consider this graph, here there is an edge s to t and there is another edge s to y. Unfortunately, there is no association from s to x directly and s to z directly. So s can cover only 2 edges, s to t and s to y. So here total number of vertices means 5. 5 minus 1 means 4. So s could have covered at most 4 edges, but due to the construction of the graph, s can cover only 2 edges, s to t, s to y. S cannot cover s to x and s cannot cover s to z, but it could have covered it provided there is an association from s to x and s to z. So in a graph, if there are n number of vertices, so every vertex can cover at most n minus 1 number of edges. Unfortunately, in this graph, it is not possible for any one of the vertices. If you consider t to x, there is an edge, t to y, there is another edge, t to z, there is another edge. Unfortunately, there is no edge from t to s. Similarly, if you consider x to t, there is only a single edge. There is no other association with x to s, x to y and x to z. Not a direct association here. Okay. So conclusion is, if there is a graph, suppose it is a directed weighted graph, if there is n number of vertices, then one vertex can cover at most n minus 1 edges. Okay. Now coming to the Bellman Ford algorithm again, though I have not expressed the logic behind Bellman Ford, just we have concluded that Bellman Ford is another single source shortest path algorithm where the graph may consist of negative edge weight, where the graph is supposed to be a weighted directed graph. Okay, so now we are moving towards Bellman Ford algorithm in detail, but before that, it is my request to everyone to go through the method called relaxation and initialization part of the graph. That means you should be very much familiar with two parameters. One is v dot d, another one is v dot pi. You know the significance already because you have already solved Dijkstra algorithm. V dot d is the shortest path estimate of a vertex v, and v dot pi is called the predecessor vertex for v. Okay, and I told you repeatedly, v dot pi accepts value which is basically a vertex, and v dot d accepts a value which is basically a numeric value. Okay, now coming back to Bellman Ford. Bellman Ford somehow uses this concept. That means if there are n number of vertices, one vertex can cover at most n minus 1 edges. This is the first one. And Bellman Ford also uses the concept of relaxation multiple times. And relaxation between what? Relaxation for all ages. That means if you summarize or if you make a brief of Bellman Ford algorithm, consider this graph again. There are a number of ages present here. Some of the age weights may be negative, no issue for Bellman Ford here. Bellman Ford applied relaxation for all ages. That means Bellman Ford applied relaxation from S to T. Bellman Ford applied relaxation from S to Y. Bellman Ford applied relaxation from T to X, T to Y, T to Z, X to T, Z to S, Z to X, Y to X, and even Y to Z. So the question is, only one set of relaxation is sufficient? That means, is it sufficient for one time relaxation? That means S to T, S to Y, T to X, T to Y, T to Z, etc., etc. No. Bellman Ford suggests under a particular iteration there should be a relaxation for all ages. That means once you start applying relaxation from S to T, S to Y and completes at Y to Z, maintaining this sequence, then it implies you have finished first iteration. Then the question is, how many iterations are there in Bellman Ford algorithm? Bellman Ford uses the concept of this one. For n number of vertices in a graph, there would be maximum n minus 1 number of edges to be covered for a vertex. That's why Bellman Ford suggests there will be total n minus 1 iteration, and under each iteration there will be a relaxation for all edges. That means in this graph there are 5 vertices. 5 minus 1 means 4. So there are 4 total iteration. Under each iteration you have to apply relaxation for all edges. That means you have to apply relaxation for the entire set. Then you complete iteration 1. Whatever updates you get, you have to use this update for next iteration. And what do we mean by update? Suppose you are applying relaxation from S to T and assume that there is a successful relaxation, S to T. There is a successful relaxation. Successful relaxation means you are expecting the D value of T is changed from its earlier value. It will accept a new value, suppose. And when D value is changing, so definitely pi value is also changing. And pi value is definitely for T, it is S, because we are assuming that there is a successful relaxation from S to T. Okay, as D value decreases, so definitely pi value is also changing. So S will be the responsible predecessor for T. So now, suppose you are applying relaxation from S to Y. It may be successful, it may not be successful, assuming that it is also successful like T. So once this part is over, whenever under the same iteration you are going to apply relaxation with respect to T to X, then you have to use this updated content. Okay, use this updated content and go for relaxation with respect to T to X. Okay, again T to Y with this updated content, again with respect to T to Z with this updated content, and so on. So basically, once there is an update, you have to propagate the update for the rest. If there is another update, suppose there is a successful relaxation for T to X, so definitely the D value of X is changing. With the update, you have to go for applying relaxation from X to T. And if in future there is again a change for T, you have to use this update. Okay, and you have to complete up to the last. Okay, so Bellman Ford, the gist is, it is a single source shortest path algorithm where negative age weight is allowed. Bellman Ford applies relaxation for all ages where there are total n-1 number of iterations, and n-1 is basically total number of vertices minus 1. If in this graph there are 5 vertices, you have to cover 4 iterations. Under each iteration, you have to apply the relaxation for all ages. Okay, Once the relaxation phase is over, you are going to enter into the next iteration. In this way, you will complete up to the last iteration. Okay, this is 70% part of the algorithm, and the rest part is very simple. You have to be, you may be worried that, sir, as the graph consists of some negative edge weight, is there any chance of having negative weight cycle? Bellman Ford have the ability to judge, is there any negative weight cycle present over the graph or not after all iteration is complete. If still there is if there is something by which Bellman Ford judges that yes, there is a presence of negative weight cycle after all iterations are over, then Bellman Ford returns false. That means no solution. Otherwise, Bellman Ford returns true. What does it mean? This means Bellman Ford have the ability to check whether negative weight cycle is present in the graph or not after all iterations are over. And how it checks? It accepts an edge again. Then check, is there any further relaxation possible? It accepts another edge and check, is there any further relaxation possible after all iterations are over? Then it leads to negative weight cycles presence. We will come to this later on, and definitely will find out how to judge the negative weight cycle in Bellman Ford algorithm. So Bellman Ford algorithm comprises of mainly two sections. One section is relaxation under each iteration, and once all iterations are over, all relaxations been complete, then the last part says, is there any further chance of relaxation, using which Bellman Ford judges that the graph consists of negative weight cycle or not. Now coming to the algorithm. Okay, so Bellman Ford solves the single source shortest path problem in general case in which edge weights may be negative, -2, -3, -4, which I have told. First part of the algorithm means Bellman Ford accepts graph G, weight parameter W, that is basically the weight function, and S as the source vertex. Source vertex may be 1, source vertex may be 2, source vertex may be any one of the vertices from the graph. Here we are assuming that in this graph S is a source vertex. That does not mean this S and this S is same. It is a symbolic representation. It indicates the source vertex name. If the vertex names are given as 1, 2, 3, 4, 5, etc., etc., then if vertex number 1 be the source, then S means 1. Okay, so S indicates the source vertex. Fine. The first step is same as Dijkstra. You have to initialize the graph. That means initialize single source method needs to be called here. And initialize single source method accepts the graph as one parameter, and source vertex must be given here. And what does initialization process means? You know it. Initialize single source means for each vertex you have to assign infinity to the d value, and you have to assign nil to the pi value. So if you have been given this graph, initialization process means s dot d, t dot d, x dot d, y dot d, and z dot d are initialized as infinity, and their pi value is initialized as nil. Then detect source. Suppose s is a source, and assign 0 as its d value. So s dot d equals to 0. This is the first step, which is similar as Dijkstra. Then the second to 4, this is what I was talking about. That means you have to apply relaxation for all edges. That means for each edge you have to apply relaxation for u to v. That's why I told in the previous section, if there is an edge from s to t, that means s comma t, then you have to apply relaxation from s to t. You have to apply relaxation from s to y because there is an edge. You have to apply relaxation from t to x, t to y, t to z. That means for each edge where the edge is formed between u and v, that means u to v, from all the edges of the graph, apply relaxation from u to v using their weight parameter. Okay, That means S to T you have to apply relaxation, where S means U, T means V, and W means 6. You have to apply relaxation. Okay, and how many times this relaxation process continues? That means how many iterations are there? Iterations means mod of G dot V minus 1. Mod of G dot V means total number of vertices in the graph, which I called is as N. N means total number of vertices. G means the graph. Dot V means the set of vertices. Mod of G dot V means total number of vertices present in the graph, which I called as N. Here in this graph, G dot V means 1, 2, 3, 4, 5. You have 5 vertices. 5 minus 1, 4. So you have total 4 iteration. Under each iteration, you have to apply relaxation for each edge in the graph. So the edge set, which I mentioned in the last section, for all edges, for each edge, first edge, second edge, third edge, and so on, you have to apply relaxation. Then one iteration will complete. Then you go for the second iteration, third iteration, and so on. This Bellman Ford suggests. So here the explanation is, given a weighted graph, ... the algorithm relaxes edges. Progressively decreasing an estimate V dot D, because you know that if there is a successful relaxation, D parameter value is always reducing, and on the weight of a shortest path from source to each vertex V, until it achieves the actual shortest path weight delta. That means unless and until it reaches to its actual shortest path weight, Bellman Ford continues the relaxation. That's why it is called progressively decreasing an estimate V dot D. Okay, and we have already known how many iterations are there and what to do. This is basically the number of relaxations under iterations. And the last part I told, you have to judge, or Bellman Ford allows us to judge whether the graph consists of negative weight cycle or not. That means after all iterations are complete, after all sort of relaxations is being done, you have to check whether still there is a hope for further relaxation. That means can you again decrease the value of V dot D? Okay, if there is a chance, that means it leads to formation of negative weight cycle. That's why the last part is very simple as the formula of relaxation. Here for each edge again U comma V, where the edge is formed between these two vertices, a pair of vertices. For all edges, if V dot D greater than U dot D plus W of UV, that means again you are applying the formula of relaxation, then return false. That means if there is a chance for relaxation for each edge, then Bellman Ford algorithm returns false. Otherwise, Bellman Ford returns true. Okay, so if 5 to 7, these 3 steps returns true, that means if V dot D greater than U dot D plus W of UV, this relationship is found false, then there is no chance of returning false. If for any edge this relationship is found true, then it will return false. Okay, that's why I am telling if 5 to 7 ultimately returns you the true result, that means this checking is somehow false for all edges. Then from 5 to 7 you are not expecting false result, you are expecting true result. That means return true. Okay, fine. So this means this algorithm returns true if and only if the graph contains no negative weight cycles that are reachable from the source. Bellman Ford algorithm returns a Boolean value indicating, Boolean value means either true or false, indicating whether or not there is a negative weight cycle that is reachable from the source. That means if this relationship is found false, or this checking is found false for all edges after all iterations are done, that means there is no chance for returning false from this block. Okay, so finally we can return true. That proves that the graph is not having any negative weight cycle, okay, reachable from the source. If there is no such cycle, the algorithm produces the shortest paths and their weights. So 70% of the algorithm completes after step number 4, but the final part, you can come to the final part after completing 5 to 7. That means you have to check whether there is a presence of negative weight cycle in the graph or not. Okay. If some cases I use the terminology pair of vertices. Pair of vertices means u comma v. This pair, which is representing an edge, u comma v, vertex u, vertex v. I am considering this as a pair, which is used to form an edge. Okay, fine. Now let us solve the problems of Bellman Ford, and I hope that after a solution of a particular problem, that would become easier to understand. So I think the algorithm is clear. First step of the algorithm means initialization, which is similar as Dijkstra. Second to fourth step is very simple, and it is basically for each iteration you have to apply relaxation for each edge. Okay, and how many iterations are there? Total number of iteration is basically total number of vertices minus 1. Under each iteration you have to apply relaxation for each edge. Okay, and this is for step 2 to 4, and last 5 to 7 is basically dealing with the presence checking is there any presence of negative weight cycle in the graph or not. For that you have to check all edges. All edges means edges of the graph. Once all iterations are complete, you have to pick up the first edge and check is there any further relaxation possible. You have to pick up the second edge, is there any further relaxation is possible, and you have to move on up to the last edge. Okay, that's why it is written as for all edges you have to check the formula. That means for this edge t dot d is greater than s dot d plus w of s to t. Is it possible? If it is possible, that means again you have a chance of further relaxation. If it is not possible, that means you don't have the chance for further relaxation. That implies you have finally achieved the shortest path estimate for t with respect to the source vertex. For this edge s to y, you have to check whether y dot d, after all iterations are over, y dot d is found greater than s dot d plus w of s to y or not. If this relationship fails, that means you have reached to the final shortest path estimate for y with respect to the source vertex. And if it is not, that means there is still a chance of decreasing the d parameter value of y. That means further relaxation is possible, though all the iterations are complete, which may lead to the formation of negative weight cycle. So this is the way to judge, and you have to check all the edges. That's why it is written as for each edge u comma v, which is formed between a pair of vertices u to v, if v dot d greater than u dot d plus w of uv, then return false. I was mentioning if this relationship is found false, that means it is found false. So there is no chance of returning false. If it is found true, then unfortunately it returns false. If it is found false, then no chance of returning false. Okay, so this is about Bellman Ford algorithm. In the next section, we'll go for solving a problem using Bellman Ford and analyze its complexity, and in the problem we will also check whether the graph consists of negative weight cycle or not. Thank you.